what we did last time was we started perturbation theory. So we're doing perturbation theory. And the basic ingredient is the transition matrix element. So you start from an initial state, you let this thing develop in time using this time development operator, and we let it start in the distant past in some initial state, move it to the future, and look at its amplitude to be in some other state in the future, some final state. And our one example so far, we have one example, is that we did first order perturbation theory of a scattering amplitude with the interaction Lagrangian being minus lambda over 4, phi to the fourth. And those phi's annihilated some states in the initial state, they created some in the final state. And if we write this transition matrix element as 2 pi to the fourth delta 4 over p initial minus p final, so overall momentum conservation came out. And then there were various normalization factors that are boring. So 2 omega 1 dot dot dot. So factors of 2 omega that have come up. And the last piece was the definition minus im. Okay, I had the minus I in front of everything, but it always comes out minus im as a definition. This ended up having a very simple form. Minus im was equal to minus 6i lambda. Okay. Last time I wasn't carrying along the minus I so much. You just had m is equal to 6 lambda. But in fact, the Feynman rules end up giving the rules for minus im. So that's what we tend to do. And to a large extent, what this is just like in perturbation theory. In usual perturbation theory in quantum mechanics, when you start off doing perturbation theory, you might do perturbation theory might have some transition. Let me call it M here also, is final V initial plus sum over intermediate states, final V and intermediate V initial over energy denominators. Okay, so plus dot dot dot. So if you develop perturbation theory in usual quantum mechanics, you end up having things like this. The first order, you just take matrix elements, so the potential. The second order, you have this sum over intermediate states, blah, blah, blah. Okay? And that's basically what we have here. This minus im, the first order, is just the matrix element between the initial states and the final states of this operator, with the exception that we dropped off the exponentials that came out. Remember, when we took this matrix element, there were e to the ip dot x's floating around. We dropped those because those went into the delta function. And there were factors 1 over 2 omega. Those go into this factor there. And what was left over was just 6 lambda. Okay, so our first attempt at this was just basically doing first order perturbation theory. Okay? Questions about that part? Our next attempt, of course, is to do next order. So what I'm going to do in this case is, so here's an example. So I'm going to mimic electron-proton scattering. Okay. Electron-proton scattering, we'll end up drawing with a picture that looks like this. An electron comes along, scatters here's a proton. There's some electromagnetic interaction between them, so at the moment this just means electromagnetic interaction in between them. And it could start off with P1, end up with P3. Proton could be P2, end up at P4. So there's some scattering amplitude there. And non-relativistically, this momentum here could be taken to be at rest, and so this proton barely moves, and the electron does all the changing directions. Since the electron is so much lighter, non-relativistically, the electron would scatter and the proton wouldn't. We'll see that limit come out of our final answer also, but we can just do this in general. Okay, so in real QED, the interaction Lagrangian is the following form. It's minus the charge on the electron, psi bar electron, gamma mu psi electron, that's the current of the electron, a mu, minus the charge on the proton's current, okay, so that's the interactions of QED that we would have gotten, the electron interacting with the photon. I'm actually planning to do a simpler case. It's you might call it the toy model. It's going to be the same thing, except that I'm going to do scalars everywhere. The trouble with this, just as a pedagogic calculation, is if I do this, I'm going to have all sorts of anti-commuting stuff that I have to worry about, and I have got all these vectors in the Dirac algebra. All of that's inessential to what we're doing. So the toy model, it just removes all the inessential stuff. We do this calculation, and then I put the real stuff back in at the end just to show you how the real answer goes. So it's going to be basically the same thing. We're going to take minus the charge on the electron, a spinless charged particle I'll call chi. So chi is a spinless particle but pretend the mass and charge of an electron, and I'll interact it with a scalar. Okay, so that scalar is like the photon. It can be massless or massive. I'll do the rules with a mass in there, and then I'll do another one, chi proton, chi dagger. This should be daggered, sorry. Chi proton, phi. Okay, so the picture is going to be the same thing. It's going to be this, and we're going to put a phi across there instead of a photon. So the real QED has a photon. Here we'll have this thing that we'll call the electron, spinless proton. And the advantage of this is just that we don't have to worry about all these factors, and like anti-commuting gamma matrices, vector signs on that. Okay. But the basic thing that is important is that these interactions don't make this transition occur to first order. You're going to have to go to second order. So our practice here is to go to second order. Okay? And let me just give you the answer so that you can see where we're headed, and then we'll do the work to get there. Okay? So it's going to come out with the same form. Minus Im is going to have the following structure. There'll be minus I times the charge on the electron, I over q squared minus m squared, minus I charge on the proton. So basically, this is the matrix element at one side. This is the matrix element to emit a phi. This is the other side. And then what sits in between is the propagator, the Feynman propagator. So this is why that Feynman propagator that we did before is important. It comes out of a calculation like this. Okay? So And to be completely fair about it, we put a plus I epsilon there because it's the Feynman propagator. It's exactly the one that we did before. Okay. Fair enough? Good. Anybody? All right, so if there's no questions about where we're headed, let's try to get there. So our time development operator here, infinity minus infinity, remember this is sometimes called the S matrix, is that time-ordered exponential of the factor is I integral d4 x times the interaction Lagrangian at x. Okay, and the meaning of that time-ordered exponential is that when you expand this, you time-order everything. So this is 1 doesn't have to be time-ordered, plus I integral d4x, the interaction Lagrangian of x. That also doesn't have to be time-ordered because there's no time, everything's sitting at one time in that, so there's no time-ordered symbol there. But we do get it at the next place. So it's then minus a half times the time-ordered product of integral d4 x li at x, integral d4 y li of y. And then there's dot, dot, dots. Okay. Well, as I said before, the first term doesn't do it for us. There's nothing in here that makes a transition from that initial state to that final state. So that guy doesn't contribute. The 1 doesn't contribute. The first piece that contributes is here. That gives a contribution. Let's just, I want to make the next line a bit simpler. So let's write this Li as the Lagrangian for electrons plus the Lagrangians for protons. Okay, and you can see that to annihilate an electron and a proton, create a final electron and a proton, I need one of these Lagrangians here has to be the electron one, and the other has to be the proton one. If both were protons, then of course you can't make the electron transition. If both were electrons, you can't make the proton transition. So you need one of each. Okay, so that little argument was to give me this factor of 2 over 2, times the integral d4x, d4y. There are two different combinations there. Time-ordered product of the interaction Lagrangian for the electrons. We can stick that guy at x. The interaction Lagrangian for protons. We can stick that guy at y. Okay, there are two equivalent combinations, but one electron, one proton. Okay? So that's our B. So we have to take matrix elements now. Yes. Yes. So the time integration in this guy goes from minus infinity to infinity. So both of these have integrations from minus infinity to infinity, and whichever one is earlier sits on this side. Okay. So you're integrating x and y at each place in that integration. You say which one's later. The early one sits here, the late one sits there. Okay, that's what the time order means. And remember how this happened is in the time development, you start over here at early times and you develop it, and the first thing that does it is the earliest thing that happens. So this time ordering comes from the fact that you propagate your quantum states from this side to that side, and that's your time ordering. Okay? All right, so now we have a couple long equations to write out. We have to write TFI, the matrix element, is, okay, so it's starts way over here with an electron with P1, a proton with P2, ends up way over on the other side with an electron of P3, proton of P4, and I stick in between there the factor minus integral d4x d4y time ordered g electron chi electron phi at x, all those guys are at x, and g proton chi proton dagger chi proton phi of y. All right, so I guess I have a little space left over there, but now we have to start taking these things. You can see that, remember, this guy has a term that annihilates the proton, so there's an a proton of P. This one has an A dagger, so that creates the final guy. And there's an A of, I'm sorry. And there's an A dagger there for electrons. Okay. Now, one advantage of doing this is that we don't have to worry about any funny business with the creation of these operators here. So the basic feature is that, you know, chi dagger E, chi E commutes with chi dagger P, chi P. So the fields associated with these guys don't care each other. This ordering doesn't make any difference. So, you know, if I order it in one time, these things all commute anyhow. Okay. The only things that don't commute are this phi and that phi. They're at different times, different positions. They don't commute. But the electrons, these guys all commute, and the protons commute with each other. So some of the matrix elements are real simple then. I just take this guy, annihilate that. I take that guy, annihilate that. This guy creates that guy. This guy goes with that. So those guys all happen, and those just turn into factors. What's left over after I do that, we've seen it a few times now, is e to the minus I p dot x, or p dot y in this case, and factors of root 2 omega. Okay, so let me write it out and we can see if there's anything that's there. So TFI is, there's a minus sign to carry along, integral d4x still d4y. Well, after I've used these guys to kill those creation operators, there's empty state. G, I get G electron e to the minus I p1 minus p3 dot x over these normalizations. Okay. Sitting over somewhere else over here, there's another number where these are just numbers now. G proton e to the minus I p3 minus p4 p2 minus p4 dot y, and I've removed all the creation operators there. Oh, I forgot all the normalizations. 2 omega 2, 2 omega 4. And the last thing that's left over is time-ordered product of phi of x, phi of y. Okay, so that still is time ordered. So again, the reason why this is such a reasonably straightforward calculation is that these guys all commute, so the time ordering doesn't make any difference. I just get numbers back for this. The only thing that you have to worry about the time ordering is the phi fields. Okay? Well, but now we've got a bunch of numbers and one last matrix element to take. That's the vacuum matrix element of time ordered product of phi to the vacuum. But that's just the propagator. So this is where the propagator enters. Okay, so we then use I df of x minus y is defined as time ordered values phi of x, phi of y. That was our definition. And that turns into, by our previous calculation, d4q, 2 pi to the fourth, e to the minus I q dot x minus y, q squared. If there's a mass, it's q squared minus m squared plus I epsilon. Okay. So now we've got all the factors, so I just take this last matrix element, that's now also this number, and grind away. Okay, so then TFI is, well, let's pull out in front G electron, Q electron, Q proton, over the square root of 2 omegas. Okay, all those factors. Then I have to do integral d4x d4y e to the minus I p1 minus p3 dot x e to the minus I q dot x minus y over q squared minus m squared plus I epsilon, and there was an I there. Actually, I missed my I, sorry. There's an I right there. If you go back, if you remember. The propagator is I over q squared minus m squared, or IDF is that. Okay, so we have that factor. Look. And then there's e to the minus I p2 minus p4 dot y. And an integral, I've got my integral d4q also. d4q over 2 pi to the fourth. Okay. Anything I'm missing? I think I got it all there, right? So we've just taken all these matrix elements, put in this function for that propagator, and we're here. Okay. Well, the x integration. The x integration gives me a 2 pi to the fourth delta 4 of, well, it's p1 minus p3 plus q, right? So I've got all the x integration is just in the exponential. The y integration gives me 2 pi to the fourth delta 4 of p2 minus p4 minus q. I've got one q integration to do. Okay, so I've got d4q But and I've got two delta functions. That just sets, then I do this Q integration. One of these delta functions sets the Q here to P2 minus P4. There's the factors of 2 pi cancel that 2 pi. And I write out TFI is, now I have minus I came from the minus sign that was overall, actually, which I forgot to copy, sorry. Let's go back up, let's get my minus signs right. There's the minus sign. And it's sitting right there, up above. It just needs to be copied. The I came from the propagator. There's a 2 pi to the fourth, delta 4. It's P1 plus P2 minus P3 minus P4 is what happens when I integrate that. I get these normalization factors, square root of 2 omega 1 up to 2 omega 4. And the rest of the stuff is the charge on the electron, the charge on the proton, times divided by Q squared minus M squared plus I epsilon, with Q is now either Q is P 2 minus P4 or P1 minus P3. I'm sorry, it's backwards. From up there, Q is P3 minus P4. P1. Okay. So this gives us what we claimed before, minus IM is minus IQE I over Q squared minus M squared plus I epsilon minus IQP. Those are the factors. And you see the I and minus I that I just added and cancel each other off. The picture that we follow for this is I've got P1 here, P2, P4. Momentum ends up being conserved at this vertex. The Q that ends up here is then Q is P2 minus P4, so I would draw it this way. I draw that this way. Q is P2 minus P4. So momentum is conserved at the vertex. So features, let's put that down written. Is conserved for momentum. Is conserved each vertex, so P2 comes in, P2 minus P4, and P4 go out. And then up at the top here, since there's overall momentum conservation, Q is also P3 minus P1. So that works here. P1 flows in, P3 minus P1 flows out, and that was a P3 flowing out. Okay. So we end up with the overall momentum conservation. So delta 4 of Pi minus Pf, again surfaced, and you can sort of see that's always going to happen. And the 1 over 2 omegas happened. But the main thing that we saw here is that the internal line became a propagator. Okay. Okay. So where we're headed is the rules that when I see this process, I just look at it and I say, this vertex is q minus iqe, this vertex is minus iqp. That line in between is the propagator in momentum space. Okay. Now, so any questions about that thing? So there's a little bit of a pain in going between there. We have a couple more painful things before we just throw that all aside and just do the Feynman rules. But this is how they develop. Yes. Did you have a question, Louise? No. Okay. Okay. So I want to tell you why you know this. You know this for various reasons. Let's first go back and think about doing this in usual quantum mechanics. So I'm going to do the Firstborn approximation. Okay. Now in the Firstborn approximation, what we're doing is you're imagining an electron comes in, scatters, P1, P3, and the proton has been reduced to just the potential. Okay, so this is some V of R that you're scattering off of. Okay, and the matrix element for this, it's a function of theta. It has some numerical factors out in front, which you only remember if you're studying for your qualifying exam. But the important piece is it's integral d3x V of R, or V of x, but generally central potential, e to the I P1 vector minus P3 vector dot x. Okay, this is the guy that we'll call Q vector. Okay, and if we're doing it scattering off of a proton, V would be the charge on the electron, the charge on the proton, over 4 pi r. Okay, you then earn, so that's the Firstborn approximation. You just take the matrix of the potential with this e to the I q dot x here, and that represents your initial wave function is the plane wave coming in, the final wave function is the plane wave going out, so e to the minus I p dot x coming in, e to the minus I p3 dot x going out, V of R. So this is my transition from my initial to my final. Okay. This guy turns into, so again, some number times QE QP over Q vector squared. Okay, so that's the same matrix element. Okay, to be fair, it's the non-relativistic reduction of the matrix element above. Q0 doesn't play a role because the energy transfer is very small. The energy in is the energy out in this case, right? So if there's no recoil, energy in is energy out. So the time components are 0. It's just the spatial components that's left. And q squared is the same, and we're putting m equals to 0 because it's a photon. Okay? So this is equivalent, the upper one is equivalent to the Firstborn approximation. Okay? But it's even more so because you would have calculated V of r as E times the scalar potential of the proton. And in principle, if you had a more complicated scattering state, you would write this as E times the integral d3x g of x minus x, let's make it x minus y, rho of y, just to make the notation similar, where this is the Green's function. Okay, and we've just made this thing the charge on the proton, delta 3 of y is equal to 0. Okay. Okay, so you would actually have calculated this thing by writing this as the Green's function, or V is given by a Green's function, and so this is really so that what we really have is implies that this f of theta is, numbers again, integral d3x, d3y. I have e to the I p initial I minus p3 dot x. Charge on the electron, Green's function of x minus y, rho of y, rho proton of y. This guy is really, psi star psi of the electron. This guy is psi star psi of the proton. And so you at this stage now you're starting to see it in the symmetric form, just like we had above, where you have the proton's wave function, the electron's wave function, the integral of the propagator in between, or the Green's function in between. This is just the non-relativistic version of the Feynman rules that we got up above, and it ends up with being the final answer. Okay, so we're doing exactly the same thing. Okay. Okay. And if you want, I can show you where the time components disappear. Our relativistic formulas had d4s. These guys have d3s, but that just comes from the fact that there's no time dilation around here, and energy is conserved across each vertex, so there's no energy transfer across the vertices. So in that limit, the propagator reduces exactly to the old famous Green's function that you know. Okay? So that's one way of looking at it. Questions about that way? The other way is the old-fashioned perturbation theory. Okay. Remember, perturbation theory says that this matrix element is in second order, is sum over intermediate states, final V, intermediate V initial, over E minus E intermediate. Okay, and what we really are seeing in this process is then these two time-ordered things we come across here, the two time orderings is either the proton emits the photon or the scalar, or the electron side does. That's what the time-ordered product of these fields is. You create a field at some point. There's some numerical factor that you annihilate it at the other point, or the reverse. So the intermediate states that you see here are just the intermediate states is electron plus a proton plus a photon. And if you really work this out in all gory detail, okay, every time I hit this point, I'm tempted to do it. It's an instructive calculation, but it's very painful, so that's why I'm not going to do it. You put in the energy differences here. So the energy difference is the initial state energy and then the energy with the photon. You put in all these matrix elements here, which have 1 over root 2 omegas in various places. You add them together, you do them just right, it comes out exactly the same thing. So this energy denominator that you see in perturbation theory turns into the propagator factor, 1 over q squared minus, it's actually just 1 over q squared plus I epsilon in the case of a photon. Okay, you can work that out in great and gory detail. But I do have to point out that there is a big difference. It's a logical difference, but it's a numerical equivalence. This way, you allow energy non-conservation. In other words, EI is not the initial energy. So the total energy of the initial state is not conserved. And so you sum over all possible energies. When you massage it and you go back and you do it the way we did it, the Feynman rules way, oops, sorry. So P was conserved, but E and P is conserved at E everywhere. Okay, and it looks different, but it's actually the exact same thing. So that's why it's fun to work out. Okay. So. All right. Any questions? All right, let's do some quick variations. Okay, let's do the real thing. Okay, so the real thing is a real electron, a real photon. There. Okay, and the answer comes out minus Im is minus I charge on the electron. It's then U bar electron P3 gamma mu U of P1. So these are the electron stuff. That was the matrix element that we got when we took electron photon vertices. That's the part of the current. Sits over here is minus IQ on the proton, U bar P4, gamma, let's make it gamma nu, U of P2. This is all the proton stuff. And then the propagator is the propagator that we wrote out for the photon, minus I G mu nu over Q squared plus I epsilon. Okay, there's no mass. And the Lorentz indices, so when that came from I d Feynman mu nu x minus y is 0 time ordered product a mu of x, a nu of y. Okay, so there's two indices associated with that, and everything else stays the same. Okay, so there's those indices there, and the currents carry Lorentz indices and spinors and all that stuff. But otherwise, logically, perturbation theory works the same. Okay. The second variation I'd like to do is let's go back to scalars just to make it simpler. So scalar case. Let's do what might be E plus E minus goes to P plus P minus. Okay. So proton, antiproton. Okay. So that would be coming in like this. Electron E minus of P1, E plus of P2. The Feynman diagram is going to be this guy, proton of P3, antiproton of P4. Okay. Well, I don't know how much is worth going through, but if you just think back of the previous calculation, we had, I can slide up here, way up here. We had the chi electron and chi dagger. This was A plus B dagger. This is A dagger plus B. So there's particle, antiparticle stuff. So this also has the possibility of creating a pair, or annihilating a pair, and this creates the proton pair. So you do that. Basically, the matrix elements just differ from those factors. You go through all the same steps there, and you write out the matrix elements. So TFI. Well, actually, let's skip that. Let's just write minus IM. In this case, is it's minus IQE minus IQP I over Q squared minus M squared plus I epsilon. And so that's exactly what we wrote before, but now Q is P1 plus P2, because if you have these lines going in, then Q is P1, Q is the sum of those, and it's the sum of the final ones. Okay. So there's how you take matrix elements. All these guys. Yes?
First line, use are operated, right?
Use? No. Use are just these. So U is just a spinor wave function. So U looks like the following. U of P is square root of E plus M over 2E times the Pauli spinor sigma dot P over E plus M times the Pauli spinor. Okay, so that's the wave function for an electron. So it's a 4-component beastie. This tells you the spin up or spin down, and so this factor up here, U bar gamma mu U, is this is a 4x4 matrix. This is a 4-component vector. That's a column vector. That turns into also a number. But it just tells you a little bit more. It tells you that as you transition from one state to the other, you have some momentum factors. Actually, I might, let me do a third example, just because we'll probably use this sometime later along too. Let's do real QED, but use spin 0 QED. Okay, so to do this, you have to remember what the matrix elements of the currents were. If I took, it's P3 current P1, okay, this current, the electromagnetic current for this guy was phi star I d mu left minus right phi, with a charge in front of it, Q. Okay, so that matrix element there we had e to the I factors, the square root of 2 omega 1, 2 omega 3, but the factor was P1 plus P3 mu. So remember, we took all these matrix elements of this current in various permutations. And I guess I need a charge floating around here, so whatever Q phi is. Okay? So the matrix element then, in the case of a scalar, would be minus Im, be minus I Q1, whatever particle 1 is, P1 plus P3 mu, minus I Q2, whatever particle number 2 is, P2 plus P4 nu, minus I G mu nu Q squared plus I epsilon. Okay. So I can't get them both on the same screen, but real QED then has this being the current, these guys being the current matrix elements. Okay. For scalars, and for fermions, it was the U bar gamma mu U. Okay. All right. Anybody else? Questions? All right. So now, before I move on to further examples, I throw a little formalism at you. This is what's called Wick's theorem. Okay, we've actually seen Wick's theorem at work. And in some ways it's very intuitive. The formal proof is a bit painful, but I won't do. But basically, in matrix elements, okay, so let's imagine you have a field phi in some matrix element. So here's some, initial state. P1. Okay, and here's a phi sitting there. Okay, maybe there's a couple of them around. That will be our case. These fields have one of two things they can do. They can either act on the external state. So this guy could annihilate that, and the other guy could create something else. Or they could act on another field in the operator. So I'm calling the operator that guy there. So this field here could annihilate that guy. Okay. So you have two choices. You either act on some external state, or you act on the other fields. So there's an or there. You can't do both. You've got an operator. And Wick's theorem is just the bookkeeping of this. Okay, So that's we have to do is tell you how to do this bookkeeping. The answer is, in the end, pretty simple. We start by defining normal ordering. Okay, normal ordering. We've got time ordering already. We want normal ordering. Normal ordering would be something that's always, it's written like this. It's phi of x, phi of y, you know, there's a bunch of fields, phi of z, normal ordering. Okay? The double dots is the normal ordering side. Fine. Okay? And you can, there's two ways of thinking about it. The operationally, the fields don't act on each other. They act only on external states. Okay, so that's what happens is normal ordering, these things never annihilate each other. The technical definition is what you do is you move all the annihilation operators to the right of any A dagger P. Okay? So why is that the right thing to do? Well, if A is on the left of A dagger, then it can annihilate this. So this annihilation operator can annihilate the state that's created by this guy. But if it's sitting up to this side here, it only acts this way, and so it only acts on the external states. It can't annihilate that guy because it's sitting off to this side here. It's annihilating something else. Okay, so technically, you just take them all, move them off to that side there. Okay, so is that enough of an explanation? I have a formula written out, which is a big long formula with just everything moves off to that side. If you have the two field operators, you move it off to that side. Okay, so what this means then is if you have vacuum matrix elements of normal ordered phi of x1 up to anything phi of xn 0, that's always equal to 0. Okay? But phi so some states, let's make it final state phi of x1. I'll just do 2 of them, phi of x2. Normal ordered initial state is not equal to 0 because these guys, the annihilation operators act on the initial state. It's not 0 in general. Okay. So with that as our definitions, here's what Mr. Jean-Carlo Wick says. Okay. He says that if the time-ordered product of phi of x, phi of y is the normal ordered product plus the propagator. Okay? So how would you prove this? Well, you would write out the time-ordered product of these two fields, and if you do that, you know, the A's are sitting on the left of the A dagger sometimes. Okay, you bring them through, put them on the right, you normal order them, you put all the A's on the right, but to do that you have to go past an A dagger, so there's a commutation rule associated with that. That commutation rule gives you exactly this. Okay, so this is when the phi's act on each other. This is basically, you know, when the piece where those act on each other goes into the time order, into that matrix element. Because you've basically removed, you know, when this A annihilates that A dagger, you're left with just something that has a vacuum matrix element. This guy doesn't. Okay, and this is consistent because if I take vacuum matrix elements of both sides, the vacuum matrix element of this side is the propagator. This vacuum matrix element is 0, so this has to be something else. Okay, that's in a way the easiest way to prove it. You just say this is normal ordered plus something, and that something has to be this guy. Okay. Wick tells us more, though. Wick also says time-ordered phi of x. Now let's make it x1, phi of x2, phi of x3 is, well, we get, there's three fields, so you get normal ordered phi of x1, phi of x2, phi of x3. So we can normal order it, and then the remaining terms are phi of x1 times time order product of phi of x. Plus phi of x2 time ordered product phi of x1, phi of x3. Clearly it has to be symmetric in all these things because the original symbol is. X1 just 1, phi of x2. Okay, so there's all the permutations of 1 left over. And that's sort of all it could be. Basically, you pair those up. Okay, and Mr. Wick tells us time-ordered product of phi. Let's for notational convenience just call it phi 1, phi 2, phi 3, phi 4. Okay, those mean x1s, x2s, x3s, x4s. Okay, they're not separate fields. Okay, well that starts off as normal ordered phi 1, phi 2, phi 3, phi 4. Then there's terms that look like phi 1, phi 2, propagator, okay. And these guys here are normal ordered themselves, so they act only on external states. And let's just write plus permutations. You know, you can do all the possible permutations of that. And then the last set of terms is all possible permutations of two propagators. Okay, so you basically always end up with propagators and things that act on external states. Okay. So this if you Wick then of course generalizes this to any time ordered products, and you can sort of write out the answer. There's the normal ordered, there's the two removed, there's the double removed ones with two propagators, etc. Okay, and it's painful to work out in general, but Mr. Wick did it once and for all. Okay, so the importance of this is it tells us that either one of two things happens. Either these fields that occur in the matrix elements work on the external states, or you end up with propagators. So basically you write out all forms of propagators that you can come up with, and fields acting on external states. Okay? Okay. So, what we need to do, the last step to do is to do loop diagrams. I can see it's not worth it all starting them out, but let's just look at what happens. Oh. Okay. We've done so far trees. These are called tree diagrams. Yeah, so tree diagrams are ones like that or like this, where things branch out. Branch out in various ways. A loop diagram would be something like this. Let's do it better. Okay, so this is the type of diagram that we'll calculate. Next is, I start with P1, P2, P3, P4, and I'm going to do this in lambda phi to the fourth, so I'm going to have minus lambda over 4 phi to the fourth at x, minus lambda at this stage over 4 phi to the 4 at y. And here's where Mr. Wick comes in. Wick, we've got all these fields here, and Wick tells us that what we do is we either let the fields act on external states, so they can annihilate these guys or create these guys, or they turn into propagators. So ahead of time we already know that these guys are going to turn into propagators. And so our goal is to use what the Wick theorem tells us and turn this into minus I m equals what. Okay? And we'll see it has some features that are the same as the tree diagrams. There'll be overall momentum conservation. There'll be normalizations that pull out for the external states, but there's going to be this extra factor, which will be a loop integral. There'll be some integral left over that's not that you have to do a full integral to calculate. It's not just a product of numbers like these guys were. So trees tend to be products of numbers. Loops tend to have an integral in it. And that's what we pull out next time, and we will, at the end of that time, write down all the Feynman rules for you. So one more somewhat painful development, and we write down the Feynman rules, and then we throw away all this development stuff and just live with the Feynman rules. Okay. Good. See you next time then. Yeah, got 2 for you. 1. There you go. Sure.